Welcome to Hart-Und-Trocken. My name is Dick Schiebon, and in this video I want to talk about the so-called rule of lHpitals. And I want to introduce someone. This is this little guy here. He's called the Hart-Und-Trocken-Män. Because it's Sunday afternoon and I got a little bored with producing these videos every day. So I thought that little guy could join me. So, well, enjoy the video and let's go. In our previous video, we were studying the behavior of functions when the independent variable x approaches certain values, like for instance singularities of the functions. That means values where the function is not defined. Also, we were studying the behavior of functions when x tends to negative or positive infinity. The different types of the behavior of the function can be that the function values approach a certain value, like for instance 0 here in the cases when x goes to negative and positive infinity. Another type of behavior is to go to negative or positive infinity, like here when x tends to negative 3. We study such functions by examining the different components of the formula separately. From this, we then conclude how the entire function behaves. For many functions, this procedure works nicely and provides the correct result. However, there are some functions where we get stuck when we use that procedure. An example is the function sin x over x. If we want to understand how this function behaves if x tends to 0, that means if we think where do the function values go if x tends to 0, and if we analyze the components of the formula separately, we find that sin x tends to 0 if x tends to 0, and also that x tends to 0 if x tends to 0. That means we have run into a situation which we may call 0 over 0, from which we can't continue, because we don't know what 0 over 0 means. Loosely speaking, the 0 in the numerator makes the fraction small, whereas the 0 in the denominator makes the fraction large. So in a way, we are not sure which one wins in that situation. That means, will the function go to plus or negative infinity? Will it tend to 0? Or will it tend just to some other limit value? Well, fortunately, we don't have to invest much work to answer that question. In fact, there is a little mathematical trick we can use in this situation, which is called lHpitals rule. Don't worry, the rule is much simpler than the name of the guy who invented it. Let me show you how it works here. The idea is to replace both the numerator and the denominator by their derivatives. That means we calculate the derivative of sin x, which is cosine x. And we also calculate the derivative of the denominator x, which is 1. Next, we replace the numerator and the denominator by their respective derivatives. So we obtain cosine of x over 1. So of course that function is not f of x anymore, so I just delete this f of x here. And now we play the same game with this new function. We think about where it tends to if x tends to 0. We examine the behavior of the components separately. So where does cosine of x tend to if x tends to 0? Well, looking at the cosine function, we find that the numerator goes to 1. And, of course, the denominator also tends to 1. So in this case, we have 1 over 1 and our standard procedure works out. This fraction tends to 1 as x tends to 0. Now lHpitals rules says that this is also the limit where f tends to. So altogether, we have lim x to 0 f of x equals 1. Let us define lHpitals rule in a precise mathematical way. lHpitals rule is given by this theorem. Let the functions f and g be differentiable in an interval alpha beta, which contains a given point a. Now suppose that f and x and g of x both tend to 0 as x tends to a. That means we have just such a 0 over 0 situation which we came across in our example before. Now if then the derivative of the denominator, that means of the function g, is unequal to 0, for all x close to a, we can calculate the limit of the function of f over g as x tends to a as the quotient of the derivative of f and the derivative of g, evaluated at x equals a. Note that the vertical line, followed by the subscript x equals a, means that we simply plug in a for x. That is nothing else than this. So now you may applaud how I dealt with the mistake on my slide. Of course, this only works if the limit of the quotient of these two derivatives exists, where by an existing limit we either mean a limit which is in the real numbers or negative or positive infinity. Loosely speaking, this condition means that our standard procedure of finding limits needs to work for this new quotient. However, if it doesn't work, we still don't need to worry, because then we simply apply lHpitals rule another time. It will get clear in the examples what I mean. Let us start with a function f of x equals x squared minus x minus 2 over x squared minus 4. First, we determine its domain, which consists of all real numbers except for those numbers at which the denominator assumes the value 0. Obviously, these are the numbers negative 2 and 2, so we have to exclude them from our domain. Now let us first understand the behavior of f of x when x tends to negative 2. We first look what happens to the numerator. If we plug in negative 2 in the numerator, we see that it tends to 4. Looking at the denominator, we already know that it assumes the value 0 when x is equal to negative 2. Now the question is, does it approach 0 from above or from below? Now, if x tends to negative 2 from below, the value of x squared is greater than 4, which is why x squared minus 4 is greater than 0. That means, in this case, the denominator approaches 0 from above, and we put a little plus superscript next to 0. If, on the other hand, x tends to negative 2 from the right-hand side, that means from above, the expression x squared is smaller than 4, which is why x squared minus 4 is smaller than 0. Therefore, the denominator approaches 0 from below. Putting everything together, we have found that f of x tends to positive infinity if x tends to negative 2 from below, and that f of x tends to negative infinity if x tends to negative 2 from above. That means that the graph of the function around negative 2 looks something like this. The bottom line is that the standard procedure for finding the limit of functions worked and we didn't need to use lHpitals rule. This will be different if we look at the singularity at the number 2. Because the problem is that if we plug in the number 2 into the numerator, we get 4 minus 2 minus 2, which is 0. That means that the numerator tends to 0 as x tends to 2. And, as we already know, the denominator also tends to 0 as x tends to 2. So we ran into the situation 0 over 0. However, lHpitals rules helps us. We apply it by taking the derivatives of the numerator and the denominator separately. The derivative of the numerator is 2x minus 1. The derivative of the denominator is 2x. Now, using the lHpitals rule, we have that the limit of f of x as x tends to 2 is equal to the limit of the new derivative expression, which means that it is equal to the limit of 2x minus 1 over 2x, as x tends to 2. But finding that limit is easy by just plugging in x equals 2. So we get 3 over 4. So we have found that f of x tends to 3 over 4 as x tends to 2. So that means the graph of f looks something like this around positive 2. Where the little circle means that there is a gap in the domain of f, which is why we don't have a function value at 2, but we could easily close that by continuously extending the function to 3 over 4 at 2. lHpitals rule is a very flexible and powerful tool. The reason for this is that it can be applied in many other situations as well. So apart from the situation we have been looking at, which is 0 over 0, we can it also use when we have the situation infinity over infinity, where it doesn't matter if it's actually negative or positive infinity. Those two are the two basic application situations for the lHpitals rule. Additionally, there are several extended applications where we can apply the rule. We will look at the following: infinity times 0 and infinity minus infinity. Let's work through several examples to get an understanding how these applications work. The first function we look at is f of x equals x squared over e to the power of x. And we want to determine the limit of f if x tends to positive infinity. By checking the numerator and the denominator, we find that the numerator x squared tends to positive infinity as x tends to positive infinity. Also, the denominator e to the power of x tends to positive infinity as x tends to positive infinity. So we have the situation infinity over infinity. Applying the lHpitals rule gives us the limit of f of x when x tends to positive infinity is equal to the limit of the quotient of the respective derivatives, which is 2x over e to the power of x. However, if we now try to follow our standard procedure, that means to once more look at the components separately, we find that still both the numerator and the denominator go to positive infinity. So obviously we still can't find the limit with our standard procedure, and we need to apply the lHpitals rule another time. So we once more build the derivative of numerator and denominator, and we get that this is equal to the limit of 2 over e to the power of x. Here we finally can apply our standard procedure because the numerator goes to 2 and the denominator goes to positive infinity, which is why the entire fraction goes to 0. Let's have a look at another example. We have f of x equals x times e to the power of negative x. And we want to calculate the limit of f of x as x tends to positive infinity. Now, as the function formula is a product, our components are factors. Obviously, the first one, x, tends to positive infinity, whereas the second one, e to the power of negative x, tends to 0. So we have the situation infinity times 0. In this situation, being an extended application of the lHpitals rule, we first need to transform the situation into one of the two basic situations, that is 0 over 0 or infinity over infinity. There are several ways to do that. For instance, we could take the second factor, e to the power of negative x, and put it into the denominator while leaving away the minus sign. This gives x over e to the power of x, which, by looking at the numerator and the denominator, turns out to be the basic situation infinity over infinity. So we find that the limit of f of x equals the limit of the quotient of the derivatives, which can be determined to be 0 by the standard procedure. And we do another example. We look at the function f of x equals x times ln of x minus 1 over x plus 1. Well, that does look a little more complicated than the previous examples. We want to know the limit of f of x if x goes to positive infinity. As in the previous example, the formula is a product and we look at the different factors. The first factor obviously tends to positive infinity. But where does the second factor go? Let's start from the interior and check where the expression within the logarithm function tends to as x tends to positive infinity. Obviously, as x increases and increases, the influence of minus 1 and plus 1 gets smaller and smaller, so that quotient tends to 1 as x tends to infinity. Now what happens to ln of this expression? Well, it tends to ln of 1, which is 0. So that entire second factor tends to 0 as x tends to positive infinity. So we have found that we have the situation infinity times 0. As in the previous example, we transform this in one of the situations 0 over 0 or infinity over infinity. Here, we take the first factor, turn it into its inverse value, and put it into the denominator. So we have a big fraction, ln of x minus 1 over x plus 1 over 1 over x. This is the situation 0 over 0. We therefore have to calculate the derivatives of the numerator and the denominator. Let's call the numerator g of x. We now need to calculate g prime of x. We could do that using a combination of the chain rule and the quotient rule. However, it is much easier if we first split up g of x using the law for logarithms, which gives us ln of x minus 1 minus ln of x plus 1. Now this version of g of x can easily be differentiated using the chain rule. As the derivative of ln is 1 over x, we have 1 over x minus 1 minus 1 over x plus 1, which using the common denominator gives this expression, which can be further simplified to this expression. Putting things together, we have lim of f of x, where x goes to positive infinity, is equal to the limit of 2 over x squared minus 1 over the derivative of 1 over x, which is negative 1 over x squared. Now instead of dividing by a fraction, we can also multiply by the inverse value of this fraction, which gives the lim of negative 2 times x squared divided by x squared minus 1. In order to find the limit of this expression, we can follow the standard procedure. In order to apply that, we reduce the fraction by the highest order of x. That means we reduce the fraction by x squared, which gives lim x to infinity negative 2 over 1 minus 1 over x squared, where 1 over x squared goes to 0. So the limit equals negative 2. And we can verify the result by looking at the graph of the function. We come to our last example of this video. We look at the function f of x equals 1 over x minus 1 over e to the power of x minus 1. Note that we have a subtraction here. We are interested in the limit of f of x if x tends to 0. As always, we look at the two components of the formula separately, starting with the first one. As x tends to 0, 1 over x tends to positive or negative infinity. Looking at the second component, we start from the inside. E to the power of x tends to 1 as x tends to 0. Therefore, the denominator tends to 0, and the entire fraction tends to positive or negative infinity. Now, in order to reduce the complexity, let us restrict to the case that x approaches 0 from above, which is why I add a little superscript plus sign next to 0. In this case, both components of the formula tend to positive infinity. So in this example, we have the situation positive infinity minus positive infinity. Also in this situation, there is a way to transform it into one of the basic situations 0 over 0 or infinity over infinity. In fact, there is a general rule which we can apply in this situation. We call the first component u and we call the second component v. So the function has the form u minus v, and the rule now is to factor out v from this subtraction so that we get v times u over v minus 1. By then simplifying this expression, we will get one of our basic situations. Let me demonstrate this to you. We write f of x equals, and now I factor out v, which is 1 over e to the power of x minus 1. Then we open the brackets and have u over v, which is 1 over x over 1 over e to the power of x minus 1. And finally, there is another minus 1. We can simplify this into 1 over e to the power of x minus 1 times, and now I interchange this numerator and this denominator by taking their inverse values. And we have e to the power of x minus 1 over x. And if I think of this minus 1 as a minus x over x, I can just add another minus x here in the numerator. And now I multiply the two fractions, which gives e to the power of x minus 1 minus x over x times e to the power of x minus 1. So, did this take us any further? Yes, it did. Because if we once more check numerator and denominator separately, we find that as x tends to 0, the numerator tends to 1 minus 0, which is 0. And the denominator tends to 0 times 1 minus 1, which is also 0. So we have indeed created the basic situation 0 over 0. Applying de l'Hpitals rule, we can write lim of f of x, where x goes to positive 0, equals lim of, followed by the quotient of the two derivatives, where the derivative of the numerator is e to the power of x minus 1, and the derivative of the denominator is, by the product rule, e to the power of x minus 1 plus x times e to the power of x. Now we once more analyze what happens to numerator and denominator. As x tends to 0, e to the power of x tends to 1, and e to the power of x minus 1 tends to 0. The same is the case for the denominator. So we apply de l'Hpitals rule once more and build the respective second derivatives, which gives lim x to 0 from above, e to the power of x, over, using the product rule, e to the power of x plus e to the power of x plus x times e to the power of x. And analyzing numerator and denominator once more, we find that as x goes to 0, the numerator goes to 1, and the denominator goes to 1 plus 0, which is 2. So we have found the final result 1/2. Let's have a look at the graph to verify that result. And we find indeed that the function approaches 1/2 as x tends to 0. So we could continuously extend f to its singularity x equals 0. So that's it for our video on de l'Hpitals rule. Thanks for watching and see you next time.